Hi, everybody. Welcome to Question Field Episode 1, the place where you ask the questions and we field them. I am Brian Buchanan.
And I'm Campbell McLaughlin.
And we are here to kick things off officially, episode number 1.
Yeah, very exciting.
Yes, very anxious. I'm very anxious as well.
Exciting producing, yeah, for sure. Yeah.
But welcome, everybody. So, yeah, Campbell, I have a question for you. And
go ahead. I think that's the idea.
Yeah. It's a simple question, but it's one of those ones where I've thought about it too much, and now my whole world doesn't make sense anymore. And what the question is, as people saw from the title, right? We're talking about dimensions, and
sure.
I want to really hone in on. Well, here's the thing, right? So I'm a high school physics teacher. Every year we end up talking about dimensions in some regard, right? Because eventually we get to motion right away, right?
Sure.
But dimensions seem like one of those things. It's kind of like gravity, right? We've lived every day assuming gravity is going to be there, and it is, and will be, right?
Very lucky, yeah.
Fingers crossed, right? And in the same way, right, we live in 3 spatial dimensions, but I feel like we kind of take that for granted a little bit.
Mm. So just to maybe summarize the question so far, like, why do we live in 3 dimensions, and what's so special about our universe?
Right. Yeah. Because here's the thing too. At some point in college, I ate from the tree of knowledge that is P-Chem 1 and 2, and I got very sick eating from that tree of knowledge because we got into talking about molecules and how sometimes they wiggle in a certain way and sometimes they wiggle in a secondary way, or sometimes they're rotating. Yeah. And we also talked about those in terms of being dimensions. And so there's this, I don't know if it's just a semantic thing. I don't know if it's just that I am just lost in the woods, or both.
I think it's an interesting question. So you're sort of getting at this idea of a degree of freedom, right? And what does that have to do with our notion of dimension or spatial dimension or something similar that we kind of know from everyday life?
Right. And and if there's like any cross between those two, like, yeah. That's my question for today. What is the proper definition, do you think, for a dimension?
It's a very good question, and I think that it kind of depends on the context that you're approaching it from. Do you have, for example, like an intuitive definition of a dimension in your head?
Well, see, I started to think of one, and then this is where the trouble starts, right? I wrote this down, right? I said a unique property that can exist in quantity. And
sure,
it's kind of a jumble of words. And it happens to rhyme.
They certainly are all words, yes.
They happen to be words. But I was thinking about even something like the game of Twister, right? We can think about how the extremities might be one dimension, the colors are another dimension, right? There are these 2 distinct things, and we can kind of pair them together.
Right. So if you were trying to describe the kind of state of your body in the game Twister, you would like say where your arm is, like what color it's on, where your leg is, and all that sort of thing. And so you could maybe, you could describe the state with a bunch of numbers, perhaps like the position of your limbs and maybe the color that they're on. Look, to be honest, I haven't played Twister in a very long time. I don't quite remember how it works.
Me either. I'm right there.
Right. But maybe that's getting at the kind of intuitive definition to have in mind, which might be the number of numbers you need to characterize a system. Right? Mm-hmm. Like, how much information do you need to properly specify a system in full?
Okay. Oh, I like.
Does that make sense?
The number of numbers needed. Yeah, that's a lot better than the unique property that can exist in quantity.
Well, I mean, I think that's a great definition for a dimension as well. But that's like one of the numbers that you need. As an example, if I have something on hand here, like a pen, I'll see me holding a pen, but
can take my word for it. Yes.
Then if I wanted to specify where that pen is, I can say like, it's 10 centimeters above the table, or half a meter away from the window and a couple of meters away from the wall. Right. 3 numbers, because we live in 3 dimensions. But the thing that you were mentioning before, going back to chemistry and thinking about molecules, is that this pen is not symmetrical. It's not like a sphere, right? So in order to characterize it more fully, I would need to say its rotational angle in space, right? Like, is it pointing towards the ceiling or the floor or one of the walls, something like that. And so do you have any sort of intuition about whether that is a dimension? Is that,
well,
what is that?
My intuition says no, but I guess where that leads me, and again, this is where I feel like I get into trouble, right? Is the universe has these 3 spatial dimensions. It has 1 temporal dimension, right? And so this is probably incorrect, but I sometimes think of the universe as like almost like beads on a string, right? And each is a slice of time. As far as I know, we don't know something like this, and I don't know if we could know something like this, but my thought goes to like, what if that bead was like rotating, 90 degrees at each slice of time, right? Would that be the rotational dimension? We would be 3 + 1 + 1, or at that point?
Right. So you're kind of thinking about this rotational angle as characterizing space in totality, as opposed to like just an object.
Right.
Is that right?
Yes.
Yeah. I mean, I think like perhaps that might be confusing things a bit, or overcomplicating, because what is space, right? I mean, we can specify points in space or the location of objects in space, but it doesn't actually matter what numbers we use to specify those points. I could say this pen's half a meter away from the wall, or I could say it's whatever half a meter is in inches and feet away from the wall.
Yeah.
So, the space itself doesn't actually exist. It's just, a set of coordinates that we place on to describe the locations of points. I mean, there's maybe a bit philosophical in that. I could perhaps get in trouble by saying that, but
it's a sense of, I guess, not to put words in your mouth, but it sounds like the context obviously matters.
Yeah, absolutely.
Okay,
absolutely.
yeah.
So it's sort of like maybe instead of thinking about a whole space rotating through time, twisting around in time, which is just the same as, something rotating.
Right.
We can just think about the objects in the space rotating.
Oh, yeah. Okay. Yeah.
Does that make sense?
Yeah. It wouldn't matter.
Yeah. You can rotate your coordinates, or you can rotate the objects inside, with respect to your coordinates. Yeah. And I think to maybe extend on this idea of like angles being something like a dimension, this is the idea behind a degree of freedom, right? An object can move in 3 dimensions of space. So there are 3 numbers that characterize its position in space. And we say it has 3 translational degrees of freedom, 3 ways that we can move it around in space. But then also if I'm holding a pen and there are 3 angles by which I can rotate it, I think, right? 1, 2. I guess there are 2 angles to specify its location on the sphere, right? So 2 angles, and that's, so those are also degrees of freedom of this pen. So there is a way that you can think about a degree of freedom as being the same as a dimension. And that's by, instead of thinking about real space, our 3-dimensional space here, you can think about something called configuration space of a system. Have you heard about this concept before?
Heard it? Yes.
Okay.
Know it and understand it? No.
Well, I think we already have a definition of it. It's just like every point in that space, in this thing called configuration space, is a unique configuration of a system. Right. So like, again, if I'm going with my pen, a unique configuration is, well, where it is in space and which direction is it pointing in. So each point in configuration space tells you where the pen is and where it's pointing. So these angles of rotation of this pen become dimensions in configuration space.
So let me see if I got this. We can go back to our game of Twister, and there's almost a configuration of like right hand red dot. Left foot, blue dot. Yeah, okay.
Yeah, that's right. So it's like the configuration is specified by where all your limbs are and what color they're on.
Okay.
Something like that.
Yeah.
Yeah, that's exactly right. This configuration space can have a different dimension than you might kind of initially expect, which is to say that there might be a different number of degrees of freedom for a system than you could than you sort of might expect from just looking at it. Like, for example, think about like a pendulum, right? So just an object hanging from a string which can move say it can move in a 2D plane, right? So you lift it up a little bit and let it swing. So it just moves in 2 dimensions rather than accessing the third. One way you could specify it, right, is by saying it's moving in a 2D plane, right? So I could specify the location of the little ball at the end of the pendulum by its XY coordinate. So that's 2. But then another way of specifying it would be to just talk about the angle that the pendulum makes with the vertical, right? So like how horizontal it is.
So how many sets, right? So either you have the one set where you have the X or the Y, or the angle itself is a set unto itself.
Yeah, that's right.
So they describe essentially the same thing.
For sure.
But I guess then also with the angle, you would need the
how far it is away from the origin or something like that.
Yeah.
So I guess we're imagining that the string is inextensible, right? You can't stretch it so that constraint, the fact that it can't move in the direction of the string, means that while it kind of looks like it has 2 degrees of freedom, this pendulum, it can move in a 2D plane.
Right.
The constraint, the fact that it can't move in the direction of the string, means it actually only has 1 degree of freedom, which you can think of as the angle that the pendulum makes. So yeah, one number to characterize the state of a pendulum means 1 degree of freedom. So what that means is that, you can think about degrees of freedom for these systems as being sort of somehow either larger than the spatial dimension or, smaller.
Right.
Particularly if you have some constraint on the system that might lower the number of degrees of freedom. Maybe it's a bit too technical. I don't know, but
I think again it comes back to this idea of so how many dimensions there are. It depends.
It depends. Yeah, absolutely. And this is kind of useful if you're if you're trying to solve this system, right? You have some equations in motion which tell you, given an initial configuration, like how is this system going to transform in time or evolve in time? And it can really help to think about these degrees of freedom, because if you realize that there are fewer than you initially expected, well, it's a bit easier to solve things in fewer dimensions. So instead of solving some 2-dimensional problem for the pendulum, you just think about, well, what's the angle? And it's a 1-dimensional problem. That's a bit easier.
We're always looking for those shortcuts.
Yeah, that's exactly right. There was just something else that I was going to refer to when we were kind of thinking about what's the definition of a dimension. And I mentioned it has to do with, well, what context you are working within. And, we've sort of discovered here that this idea of a degree of freedom can also depend on the context of the system. But dimension can mean slightly different things depending on what field you're working within, and we're working within question field, but but if you're for example, if you're a mathematician, which I'm not, but I've heard of some concepts that mathematicians throw about, they could be referring to different things if they're dealing with different objects. But what's interesting is that this idea of a dimension really is quite universal in math.
Right, yeah.
Like if you have vector space, which is something, you can think of a vector as being a little arrow which has a length and a direction. And the space that a vector lives in is called a vector space.
Right.
And a vector space has a dimension, which is very easy to think about because it's very intuitive. It's just basically the same as the dimension of space that we live in. Yeah. It's slightly different from the formal definition that other spaces have. For example, you can get some really weird definitions of dimension, like if you ever work with fractals, right? You've heard of fractals?
Yeah.
They can have a certain definition of dimension, which is not an integer. So you can have a 3/2 dimensional fractal.
I gotta wash my hands.
It gets pretty weird.
Yeah.
But yeah, there you go.
Wild. Sorry, I'm still flustered by 3.5.
No, that's okay.
Fractal dimension. Yeah. It's just it's just all fascinating to me. It's fascinating. So,
can I ask you a question?
Absolutely.
Why do we care about these things? Why do we care about the number of degrees of freedom that something has, or I guess it's maybe a bit more intuitive why we care about the number of dimensions something moves in, but what about degrees of freedom? Why bother counting them?
I feel like there's some wanting to know the many combinations that something can occupy.
Sure, maybe fully understand, what characterizes this system. if you think about the way molecules and atoms move, they can be sort of to a very good approximation thought of just moving kind of randomly. And so if you think about the ways in which a molecule can move and think about sort of like a just random motion in all of those directions, then that gets you a pretty good way to understanding how it actually moves in practice. So if you think about all these ways that a molecule can move, you start to think about the properties that a whole bunch of these molecules can have. So like if you have molecules forming a gas, something like that. There's a theorem which says that if you have a certain type of a degree of freedom, then the energy of a system is equally chunked into all of those different degrees of freedom. So if I have if I have my pen, and we're thinking about this as a tiny microscopic pen, and it's a statistical system, so there are billions and billions and billions of these tiny pens, then if that whole system has some amount of energy, then on average, some of that energy gets put into moving these pens about in space, and some of that energy gets put into rotating them. So it's sort of like 3 lots of that energy gets put into the kinetic energy of these pens, just them bouncing about frenetically. And then 2 lots of that energy gets put into spinning them about, like if you're doing some cool pen trick with your fingers, which I can't do. So if you learn some stuff about thermodynamics and things like that, you learn about all these different things, like, for example, specific heat. How much energy does a substance take, like water, for example? How much energy do you need to put into water to raise its temperature? And you can think about specific heat either as some just macroscopic property, which is just, given to you. Like you don't need to derive it. You just kind of measure it and that's it. Or if you think about these degrees of freedom, you can actually kind of derive the specific heat
by just accounting for each different way that it can move, and what's the proportion of how many are going to be moving this way. And
that's exactly right. Yeah. Do you teach this kind of stuff to your students?
Not even a little bit. No, we no. I think when I talk about dimensions practically, it's kind of like, all right, what is it that you have to account for, right? When we're running, we're trying to measure a cart going down a ramp. We got to know the angle of the ramp. We got to know the length of the ramp. We need to make sure we have our stopwatch, right? It's just, what is everything that we got to make sure we have, right? That's like probably the extent of how far like we get into it. And certainly not to this dare I say degree of of conversation or depth of conversation.
Yeah, right. But you can, I guess, see where the more technical or formal aspects of dimension come into play in those discussions, right?
Yeah.
Oh, like you're talking about the angle of the ramp and the length of the ramp, and those are all numbers that you need to describe the state of that system that you're dealing with. So they're in some sense like degrees of freedom or dimensions of that system. Are you able to describe a bit more sort of your thought process when you started maybe thinking too much about this topic?
Once I felt like I had a stronger idea of space-time, this 3+1, which I'm not saying I understand right or well, but to the extent that I ever did, it was kind of like, what else could be a dimension? And I try and read science articles when they come out, and you hear stuff about, there's 10 or 11 dimensions in string theory, depending on the particular flavor. And it's like, well, then where are they? Where are they?
It's an interesting question. Like, why is, even before you get to the craziness of string theory, regardless of whether or not it's true, why is time considered a dimension?
Yeah. Campbell, why is time considered a dimension?
Well, I'm glad you asked, Brian. Well, I guess, so this idea comes broadly from special relativity. I mean, these ideas were sort of percolating around the time that Einstein summarized them in his 1905 paper. The reason, well, maybe let me ask you this. Imagine you have an object, and I seem to be gravitating towards my pen today, so I'll stick with this. And I rotate that object, right? So say it's pointing initially in the X direction, and I rotate the pen around the Z axis, right? So it's now pointing somewhere between like X and Y, right? So you can sort of think about this rotation as mixing the X and Y directions. Does that make sense to you?
I'm processing it. Yes, I think that tracks.
So sort of like the length of the pen isn't changed, right? By rotating it. But some of that length is now in the Y direction where it was initially all in the X direction.
All in the X, yeah. Yeah, it's what is the proportion that has now been shimmied or traded or whatever, however, yeah.
That's exactly right. Yeah, what's been traded between the X and Y directions. And so if you say, for example, you were here, you had your set of coordinate axes, and according to you, the pen was pointed in the X direction. Whereas for me, I have my own coordinate axes. Maybe I have my own rulers and whatever else. And I say, no, that pen's pointed halfway between the X and Y direction. And you say, well, that's okay because we have a difference in perspective, but that's okay. We all agree, for example, on the length of the pen. If we can disagree on where it is pointing with respect to our coordinate axes, but we all agree on the length. Right. And so what physics cares about are these quantities that don't change when you go into a different observer's perspective. Like if you ask Brian what the length of the pen is, he says the same thing as if you ask Campbell. And the key realization was thinking about the speed of light as being something that all observers agree on. And so that's important, right? Because again, that's what physics is kind of about. But it turns out that if that's something that all observers agree on, then you can think about maybe what happens if I send out a beam of light and you are traveling at 99% the speed of light, according to me, in the same direction. And I ask, well, what speed do you measure that light to be traveling at? And it's got to be the same speed, right? Which is kind of weird because you would think you would measure it to be 1% of its speed, according to me. So there is a specific set of transformations. So again, that rotation that we were talking about is a transformation from my set of axes to your set of axes. And that transformation was just a rotation. There is also a transformation that gets from my set of spatial and time axes, sitting here still on Earth. And there's a transformation that gets from that coordinate system into your coordinate system, which is also a set of axes and a clock to measure time. So all of that is to say that because the speed of light is constant, then we need this weird transformation that gets between the coordinate systems of observers that are moving relative to each other. So if you're moving 99% of the speed of light, we need some transformation that gets from your frame of reference, your sets of axes and your clock to mine. And that transformation is called a Lorentz transformation or a Lorentz boost. Boost because it like boosts your speed.
Right. So to bring this back to your pen, the length of your pen in this analogy is the speed of light because that is the thing that we agree on.
Sort of. It's let me just connect it directly to the pen. The length of the pen is now something called a space-time interval. And the reason that we need a space-time interval is because that is what's preserved by a Lorentz transformation. So in the case of a rotation, the length of the pen in three-dimensional space was preserved by that rotation. Now we have this thing called a Lorentz transformation, which preserves the length of my pen, which is pointing in four-dimensional space-time.
Okay.
Yeah. Okay. So it's very difficult to think about, and particularly because we, are on a podcast, we can't have visuals.
Yeah.
It's exactly the same. It's just like if you replace the z-axis with a time axis, then the Lorentz transformation is again just a rotation, just as you would normally think about, and the length of the pen is the same. But it is it's very confusing because now we're thinking about the length of a vector pointing in time as well as space. So the reason we need to think about time as a dimension is because the thing that we all agree on is this space-time interval. We don't agree on spatial length anymore because this is one of the results of special relativity. If you are moving really, really quickly with respect to me, I will see your rulers get shrunk. So that's called length contraction. So this is really, it's insane. It's mind-boggling. But and so I'm just sort of saying this like it's blasé or, so 1905, but it's amazing. But yeah, we'll hopefully we'll talk about it.
Oh, I'm sure. You don't know the number of questions that this one episode is going to generate.
Yeah, so we don't agree on spatial lengths anymore. We also don't agree on durations anymore. If I measure something to last 1 second and you're moving really quickly, you'll measure the same thing to last much longer. But the thing that we do agree on is this combination of space and time. It's like if we observe or take as a postulate, right, that the speed of light is constant, then you say, well, okay, fine, but what are the consequences of that? And the consequences are in part that this space-time interval of this pen pointing in space and time has a length which is preserved. And it's sort of like the speed of light being constant is really important. It's fundamental, but it's also like once you accept it, it's sort of like, okay, but now who cares? Like the next step is the kind of thing that you work with more. And that next step is that these vectors which point in space and time have a length which is preserved. And by preserved, I mean all observers agree on. I guess
what it sounds like, once you have both of those components, you can kind of go in either, I shouldn't say either direction, right? But you can kind of they point to each other in a way that feels satisfying.
Yeah, absolutely.
Campbell, I think we need to take a breather for a week and let the listeners recover, because I, of course, am right there with you on all this. If we could pick this up next week and we'll take it.
Absolutely. I think we've got some more stuff that we can actually talk about on this related to this question. But I will say that obviously this is just, these podcasts are kind of just discussion around a question, right? We're not teaching you, we're not like giving you some rigorous introduction to any topic. We're just kind of mulling things over and that sort of thing. So if it brings up any questions, I'm sure we'll have some way for you to write in and share us your own questions.
Absolutely.
Share with us your own questions.
Absolutely, yes. All of that information will be in the description, ladies and gentlemen. And yeah, we would love to hear from everybody.
Yeah, certainly if we've made any mistakes, which I'm sure through the episodes will be the case, let us know about that as well.
Please, yes. Send all your hate to this email address, which I'll splice in right here. But thank you for listening, everybody. We will be back next time, picking right back up with Dimensions.
You've been listening to Question Field. Question Field is a Gain Media production and is produced by its hosts Campbell McLaughlin and Brian Buchanan. For more information, please check us out on Instagram at QuestionFieldPod, on Twitter at QuestFieldPod, and on TikTok at QuestionField. If you have a question you'd like to submit, or would simply like to leave a message, please send us an email at questionfieldpod@gmail.com. Recently, the James Webb Telescope discovered 5 new stars, located in the review section of your favorite podcast app. Thank you for listening.